Performance, unlike Hanyuan 1's already well-documented, independently referenced fidelity numbers. A brand new startup's own claims presented at a trade show deserve real scrutiny before you treat them as settled fact. And that scrutiny simply hasn't HHH for 2 decades. A single rule governed every quantum computer ever built. Get close to functioning and you needed cold, not winter cold, not freezer cold, colder than the empty. Space between stars, a fraction of a single degree above absolute zero, maintained inside a machine that costs millions of dollars and fills an entire room. That rule just broke. Not in one lab, but in at least 5. On 3 different continents, using at least 3 completely different kinds of physics, all within the same 12-month stretch. A quantum computer built in Germany has been running nonstop since June of last year, sitting at ordinary room temperature, and it's already beaten the performance numbers its own customer wrote into the purchase contract. Read that again. Nobody expected this rule to break this fast. To understand why this moment deserves your attention, you first have to understand exactly what quantum computers have been fighting against since the very first working qubit flickered into existence in a laboratory decades ago. A qubit, the basic unit of quantum information, is almost unbelievably delicate. Unlike the transistors inside your phone, which sit stable and predictable through years of ordinary use, a qubit can lose its entire quantum state from something as small as a single stray photon brushing past it, or the faintest whisper of ambient heat. And heat is everywhere. At room temperature, every atom and every material around you is constantly jittering, vibrating, colliding with its neighbors in a chaotic dance physicists call thermal noise. For most kinds of qubits, that noise is loud enough to instantly destroy whatever fragile quantum calculation was underway, the same way static on a phone line can drown out a voice you're desperately trying to hear. For the better part of 30 years, the industry's answer to this problem was almost brutally simple. If heat is the enemy, remove the heat entirely. Build a dilution refrigerator, a machine capable of cooling a chip to temperatures colder than deep space, and keep your fragile qubits sealed inside it for as long as the computer needs to run. This is not chaos. This is strategy, but it's an expensive strategy, one that has quietly kept quantum computing locked away inside a small circle of national laboratories and trillion-dollar technology companies, the only institutions on Earth that could realistically afford the infrastructure this approach demanded. What most people are not seeing is that an entirely different school of thought has been developing in parallel this whole time. One built on a simple, almost stubborn question. What if, instead of fighting heat with brute force refrigeration, you built a qubit that simply didn't care about heat in the first place? That question sat mostly theoretical for years, discussed in physics papers and pursued in small, underfunded labs, while the flashier superconducting approach captured most of the headlines and most of the investment. And then, throughout 2025 and into 2026, that quieter research thread suddenly, almost simultaneously, started producing real, working, commercially deployed hardware, arriving from multiple independent teams within months of each other as if the entire field had crossed some invisible threshold all at once. Let's begin with the company that's furthest along this specific road, because understanding exactly how their hardware works tells you everything you need to know about why this breakthrough is physically possible at all. Quantum Brilliance, a company spun out of the Australian National University back in 2019, took an approach that sounds almost deceptively simple once you hear it explained. Rather than isolating a fragile quantum state and then burying that state under millions of dollars of cryogenic protection, the company builds its qubits directly inside synthetic diamond using something called nitrogen vacancy centers. Picture the atomic structure of a diamond, an extraordinarily rigid, tightly bonded lattice of carbon atoms, among the hardest, most stable materials found anywhere in nature. By deliberately removing a single carbon atom and replacing its immediate neighbor with a nitrogen atom, physicists create a tiny, precisely engineered defect inside that lattice, a pocket where a genuine quantum state can exist, shielded not by extreme cold, but by the sheer physical rigidity of the crystal surrounding it. Andrea Tabacchini, the company's VP of Product and Marketing, described exactly why this matters in a single, quietly devastating sentence to the technology outlet Fierce Network. It means we have long enough coherence time, so long enough usability of the qubit, even without the need of cooling down. Think about what that sentence actually undoes. 30 years of assumed physical necessity, dismantled by a defect deliberately engineered into a diamond. This isn't confined to a laboratory bench somewhere either. In late 2025, Quantum Brilliance installed a small cluster of 3 of these room temperature quantum computers directly inside Oak Ridge National Laboratory, one of the flagship research facilities operated by the United States Department of Energy. According to the lab's own description, the cluster sits inside a rack that looks remarkably similar to an ordinary data center server rack, a detail worth sitting with for a moment because it represents a real physical answer to a question the entire quantum computing industry has been asking for years. Can quantum hardware actually sit inside a normal computing facility, right alongside the classical servers already running there, without a dedicated cryogenic wing standing between them? Ashley Barker, who directs Oak Ridge's Leadership Computing Facility program, framed the collaboration's goals in strikingly unglamorous practical terms, describing work on co-scheduling, end-to-end performance tuning, data and workflow orchestration, workforce development, and more, all aimed at eventually moving what she called HPC quantum integration from a conceptual pilot to a fully embedded capability within leadership computing. Notice everything that's absent from that description. No mention of a new cooling facility, no mention of specialized cryogenic infrastructure. Just the ordinary patient engineering work you'd expect once the cooling problem has already been solved. Before this story goes any further, though, it deserves the same honest scrutiny we owe every genuinely exciting scientific claim. Because getting the excitement right means being equally honest about the limits. Tabaccini himself didn't try to oversell what his company's diamond-based hardware has actually accomplished so far. Eliminating the temperature problem, he explained, is not the same thing as eliminating quantum computing's other deep, stubborn challenge, the problem of noise and error correction more broadly. A fault-tolerant quantum computer is really what one needs for true commercial-scale reliability, he said, adding that even a perfect quantum computer is still subject to noise, beyond simple thermal vibration, and that developing the error correction algorithms needed to fully manage that remaining noise is, in his own words, going to take a while. This is precisely the kind of candid, unhurried honesty that separates a genuine scientific breakthrough from an overhyped press release, and it's worth remembering throughout the rest of this story. While that harder, longer-term problem continues to get solved, quantum brilliance is generating real near-term revenue from a narrower, already useful application of its diamond qubits, high-resolution quantum magnetometry, essentially turning these room temperature qubits into extraordinarily sensitive magnetic field sensors for industrial, transportation, and healthcare uses. Now travel with me to Germany, because a second, entirely independent player has just pushed this same underlying idea considerably further, and the scale of what they've built changes the shape of this entire conversation. In July of 2026, a startup called Saxon Q announced the commercial launch of two systems, the SXQ128 and the SXQ512, scaling up to 128 and 512 qubits, respectively, built on the same underlying diamond nitrogen vacancy architecture pioneered by companies like Quantum Brilliance, but pushed decisively past the small, laboratory-scale qubit counts the field had been stuck at for years. According to the company's own materials, these represent the first diamond-based quantum systems to meaningfully break past 10 qubits while still operating entirely at room temperature, with no cryogenic cooling, no vacuum equipment, and no specialized facility of any kind required. And unlike so, many quantum computing announcements that arrive as pure press releases with no real customer behind them, Saxon Q's claims come with genuine, independently verifiable, real-world backing. A respected German applied research institute called Fraunhofer IWU has been running one of Saxon Q's mobile quantum systems continuously since June of 2025, using it for industrial optimization problems in material processing and robotics. Albrecht Hennel, who leads digital production twin research at Fraunhofer IWU, offered a piece of validation that's genuinely rare to hear in this field, an actual customer publicly exceeding their own expectations rather than cautiously hedging them. The system has operated at room temperature continuously since installation, he said, and has exceeded the gate fidelity specifications we outlined in the tender. Read that again, slowly. Not met expectations, exceeded them over more than a year of continuous, real-world industrial use. While diamond-based qubits have been making their steady, methodical progress across Europe and North America, an entirely different physical approach has been advancing at a genuinely startling pace on the other side of the world, and understanding it means setting diamonds aside entirely and picturing something stranger, individual atoms, suspended in midair, held perfectly in place by nothing but the pressure of laser light. This is neutral atom quantum. Computing and China's progress in this specific corner of the field over the past 9 months has been remarkable simply for its sheer speed of iteration. In October of 2025, a company called Zhongke Kuyuan, affiliated with the Chinese Academy of Sciences, delivered a system called Hanyuan-1 to a subsidiary of China Mobile, marking the country's first commercial neutral atom quantum deployment. The specifications are genuinely competitive on their own technical merits, 100 qubits, running entirely at room temperature, the whole system compact enough to fit inside just 3 standard equipment racks, with single qubit gate fidelity of 99.9% and 2 qubit gate fidelity of 98%, numbers that hold their own against far more expensive cryogenically cooled competitors. This wasn't merely a government showcase built for headlines. The system generated roughly 40 million yuan, close to $5.6 million, in genuine commercial orders, including an international sale to Pakistan specifically to establish that country's first national quantum computing center. And by December of 2025, Zhongke Kuyuan had secured strategic financing from the China Mobile Chain Leader Fund, the kind of sustained institutional backing that signals real, ongoing commercial confidence rather than a single publicity moment. The pace didn't slow down from there either. Just 7 months later, in May of 2026, the same research lineage unveiled Hanyuan 2, redesigned around a dual-core cabinet architecture that requires no ultra-low temperature cooling environment whatsoever, with total power consumption held under 7 kilowatts, an almost absurdly modest energy footprint for a working quantum computer, roughly comparable to running a handful of ordinary kitchen ovens at once. Then, just 2 months after that, at the World Artificial Intelligence Conference in Shanghai, a brand new company called Zhongqi Wuliang, a spin-off from the Chinese Academy of Sciences Shanghai Institute of Optics and Fine Mechanics that, according to industry reporting, simply didn't exist a year earlier, unveiled a system called Qinghe No. 1, pitched explicitly as a quantum computer built to slide directly into an ordinary server rack. No dilution refrigerator, no vibration isolation table, no dedicated quantum facility required at all. Here's where honest reporting has to pump the brakes, though, because not every claim in this fast-moving space has been independently verified yet. As of the most recent available reporting, no independent benchmarks have confirmed Qinghe No. 1's actual peeping yet for this particular machine. There's a deeper, more fundamental layer of science underneath all of these individual commercial announcements, one that helps explain why this breakthrough is arriving from so many independent directions simultaneously, rather than emerging from a single research group getting lucky. At Stanford University, researchers demonstrated something genuinely foundational: room temperature entanglement between a single photon of light and a single electron, achieved directly on a chip built using silicon-compatible manufacturing techniques. The team pulled this off using an elegant combination of twisted light, a two-dimensional material called molybdenum diselenide, something called Valley States, and carefully engineered silicon nanostructures, creating stable quantum interactions with no dilution refrigerator involved at any stage. It's worth being precise about exactly what this represents, because overstating it would do the actual science a disservice. This is not by itself a working quantum computer. It's arguably something more foundational than that, proof that entanglement itself, the strange linking of two particles' quantum states across space, one of the core physical phenomena every quantum computer ultimately depends on, can be reliably created and sustained at ordinary room temperature, using manufacturing methods the existing semiconductor industry already understands. Think about what that specific detail implies for the future. If the fundamental building blocks of quantum information can be created using silicon-compatible processes, the eventual path toward manufacturing quantum hardware at true industrial scale starts to look less like inventing an entirely new industry from scratch, and more like extending a manufacturing playbook the world has already spent 70 years perfecting. A closely related discovery arrived just weeks later, adding yet another independent thread to this rapidly accumulating body of evidence. Physicists created what they describe as the first genuinely room temperature quantum material, a plasmonic structure called a quantum statistical metacrystal, built from gold meta-atoms arranged with extraordinary precision directly onto a chip. This material operates at room temperature while selectively transmitting and routing distinct quantum states of light, functioning as a kind of quantum statistical filter, preserving quantum coherence and enabling robust transport of quantum information without any cryogenic cooling at all. To appreciate why this matters, you have to appreciate just how unusual it is within the broader landscape of quantum material science. Nearly every quantum material discovered up to this point reveals its most useful, most remarkable properties only when cooled close to absolute zero, because at room temperature, the constant thermal jitter of atoms simply drowns out the delicate quantum behavior. Researchers are trying to study and control. This metacrystal sidesteps that entire problem through geometry, through the deliberate physical arrangement of its structure, rather than through brute force refrigeration, and its creators frame the underlying design principle as generalizable, with potential applications reaching beyond quantum computing entirely, into fields like quantum information processing, and even improved solar energy conversion. Step back for a moment and look at everything you've just heard laid out side by side on the same timeline, because the pattern that emerges is more significant than any single result on its own. An Australian-founded diamond qubit company deploying real hardware inside a U.S. national laboratory. A German startup launching commercial systems that are already exceeding customer performance specifications in genuine industrial use. Multiple Chinese research spin-offs iterating at a genuinely startling pace. A 100-qubit commercial launch followed 7 months. Later by a dramatically more power-efficient redesign, followed 2 months after that by an entirely new company's server rack compatible system. Stanford, proving the foundational physics of room temperature entanglement, works on silicon-compatible hardware. A separate team engineering an entirely new room temperature quantum material from gold nanostructures for a different purpose altogether. This is not one lucky laboratory stumbling onto an isolated result. This is what it looks like when an entire scientific field crosses some kind of collective threshold at roughly the same moment, when decades of accumulated groundwork finally mature to the point where multiple, genuinely independent teams pursuing entirely different physical approaches arrive at remarkably similar conclusions within months of each other. So why does any of this actually matter beyond the pure scientific novelty of watching several labs solve the same hard problem in parallel? This is exactly the point in the story where an honest documentary has to confront its own title directly, because getting this part right matters far more than chasing an exciting but inaccurate framing. Does eliminating the cooling requirement genuinely mean classical computers simply can't compete anymore? The honest, carefully researched answer is more nuanced than that framing suggests, and the nuance itself turns out to be the more useful, more interesting story. What room temperature quantum computing has genuinely, verifiably solved is a massive, expensive, deployment-limiting engineering bottleneck, not some fundamental computational contest between quantum and classical machines. For nearly 2 decades, the extreme cooling requirements built into leading quantum architectures, the kind used in Google's Willow chip, IBM's fault tolerance roadmap, and Quantinuum's trapped ion systems, kept quantum computing locked inside a small circle of elite national laboratories and trillion-dollar technology companies, the only institutions capable of affording a multi-million-dollar dilution refrigerator and the specialized facility required to house it. Room temperature quantum computing genuinely threatens to dismantle that specific barrier, potentially opening access to universities, mid-sized research institutions, and companies that could never have justified that kind of capital expenditure before. But here's the honest concession this excitement demands before it fully earns your trust. Removing the temperature barrier does not automatically solve quantum computing's other equally stubborn challenges. As Quantum Brilliance's own team was refreshingly candid about, thermal noise is only one of several distinct categories of interference threatening a qubit's fragile quantum state, and building genuinely fault-tolerant error correction remains a substantial, unfinished engineering challenge, regardless of whether your qubits happen to sit inside a dilution refrigerator or comfortably on a laboratory bench at room temperature. Even some of the most commercially motivated voices in this industry remain openly skeptical about the pace of near-term deployment. Amazon Web Services has publicly described the entire idea of simply racking and stacking quantum computers directly inside an ordinary data center as, in their own blunt characterization, closer to fantasy than near-term reality, a genuinely useful counterweight to include here, precisely because it comes from a company with every commercial incentive to want quantum computing to succeed as quickly as possible, and even they remain cautious about the timeline. And here's the deeper truth. A fair, balanced telling of this story has to acknowledge honestly the exact point where the classical computers can't compete. Framing from this video's own title needs real tempering. None of these room temperature systems, not Quantum Brilliance's diamond qubits, not Saxon Q's 512 qubit SXQ 512, not Hunyuan 2's remarkably efficient 7 kilowatt cabinet, currently outperforms classical computers at the overwhelming majority of everyday computational tasks, and none of them are remotely close to doing so in the near future. Quantum computers, room temperature or otherwise, remain fundamentally specialized instruments, genuinely powerful for a narrow set of problems involving optimization, certain categories of chemistry and material simulation, and specific mathematical structures that happen to align naturally with quantum mechanics, while remaining meaningfully worse than an ordinary laptop at the vast majority of ordinary computing tasks, running an operating system, browsing a website, or processing a simple spreadsheet. What room temperature quantum computing genuinely changes isn't the fundamental balance of computational power between quantum and classical machines. It changes where and how cheaply the specialized quantum tool can physically be deployed in the first place, moving it out of an isolated laboratory environment requiring millions of dollars of supporting infrastructure, and into something that could eventually sit inside an ordinary server rack in an ordinary building, needing nothing more exotic than the electrical outlet already installed on the wall. Think through the practical implications that actually follow from that more modest but still genuinely significant shift. A university physics department that could never justify purchasing a multi-million-dollar cryogenically cooled quantum system might genuinely afford a room temperature alternative instead, bringing serious quantum research capability to institutions that have been entirely locked out of this field for decades. A mid-sized manufacturing company, exactly like Fraunhofer, IWU's real-world deployment for material processing and robotics. Obsolete. All of it represents quantum computing finally, genuinely beginning its slow, methodical transition from an isolated laboratory curiosity into something resembling ordinary, deployable, industrial infrastructure, sitting comfortably alongside the classical computers it will most likely keep working with, rather than replacing, for many years still to come. There's a geopolitical thread worth pulling on here too, one that connects back to the broader technology competition between the United States and China we've explored in previous videos on this channel. The fact that China has managed to iterate through 3 distinct room temperature neutral atom systems within roughly 9 months, moving from an initial 100-qubit commercial deployment to a dramatically more power-efficient redesign to an entirely new startup's server rack compatible architecture, reveals a genuinely aggressive, well-resourced national push into precisely this corner of the quantum computing landscape. Room temperature neutral atom systems sidestep one specific supply chain vulnerability that has shaped much of the broader US-China technology competition: dependency on specialized Western manufactured cryogenic refrigeration equipment. Exactly the kind of dependency that export controls are typically designed to exploit. By pursuing an architecture that simply doesn't require that particular category of imported hardware, Chinese quantum computing companies may be deliberately building around one of the most effective points of Western technological leverage over their broader ambitions in this field. A pattern that echoes what we've already documented in other corners of China's quantum hardware development. So where does all of this leave us, watching this genuinely fast-moving story unfold across 3 continents throughout 2026? The honest, carefully researched answer is that room temperature quantum computing represents a real, verified, independently confirmed engineering breakthrough, substantial enough to genuinely reshape who gets to access quantum hardware and where that hardware can physically live, without requiring the kind of massive capital expenditure that has locked this technology inside an exclusive club of elite institutions for the better part of 2 decades. But it does not, as of the middle of 2026, represent classical computers, somehow becoming unable to compete, a framing that overstates what any of these individual systems have actually demonstrated so far. What these breakthroughs genuinely prove is that one of quantum computing's oldest, most expensive, most deployment-limiting physical barriers is finally, verifiably starting to fall, opening the door to a future where quantum and classical computers might eventually sit inside the very same server rack, solving different halves of the very same problem, rather than competing head-to-head for the exact same job. If you want to understand exactly what happens once these room temperature systems finally combine with the kind of quantum error correction breakthroughs we've covered in earlier videos on this channel, the moment when the temperature problem and the noise problem both finally get solved on the very same piece of hardware, that's precisely the story we'll be tracking closely as it continues to develop. So make sure you're subscribed before that. Convergence finally arrives. Before you go, I want to know what you honestly think about everything you've just heard. Does eliminating the need for extreme cooling feel like the breakthrough that finally brings quantum computing out of the laboratory and into ordinary everyday deployment? Or do you think the harder, less glamorous problem of quantum error correction will keep this technology confined to specialized applications for years to come, no matter what temperature the hardware happens to run at? Leave your honest answer down in the comments below, and as always, I read every single one.